of a gas is directly proportional to temperature. Mm, V is directly proportional to T. V is directly proportional. I think I made a mistake over here. No, pressure is not directly proportional. Pressure is inversely proportional to volume, right? If I increase the pressure, the volume would decrease. Don't you think so?
No. If we increase pressure.
Hmm. I made a mistake over here. So if we let me rewrite this whole thing. 1 second. Hmm. Okay. Again, for pressure of a gas is inversely proportional to volume. P is directly proportional to 1 by V. And this gives me that P is equal to constant by V,
Mm.
and PV is equal to constant. So product of pressure and volume is constant. So this means that if I've got a gas with initial pressure P1 and that at that initial pressure P1 volume is V1, if I change the pressure to P2, the volume would accordingly change to V2, right?
Hmm.
Hmm. So P1 V1 would be equal to P2 V2. Then the next thing that I've got after this is temperature law. Just 1 second. Hmm. The one after this is temperature law. So for temperature law, volume of a gas is directly proportional to the absolute temperature. Alright. If I increase the temperature, the volume would increase, and if I decrease the temperature, the volume of the gas would decrease. Agreed?
Yeah.
Okay, so this means that volume is equal to constant into temperature. So volume by temperature is equal to constant. So this means that ratio of volume to temperature of the gas, it remains constant. If I change the, so if I've got V1 by T1, if I change the temperature to T2, the volume would change accordingly, so that this ratio it remains intact of the ratio of V1 to T1. All right.
Hmm.
PV. Hmm. Hmm. And the last one that we have is pressure and volume. We have done volume and temperature. We have done. Is there a third one in your book? I mean, is the third one in your book or not? P is directly proportional to 1 by V. Okay. Okay, so combining this pressure and temperature, there is this pressure and temperature. So the third one is pressure is directly proportional to temperature. So if I increase the pressure, the temperature, sorry, if I increase the temperature, the pressure would increase.
Okay.
If I increase the pressure, the temperature, if I increase the temperature, pressure would increase. So this gives me that P by T is equal to constant. Okay, so if I combine all these three that I've written until now, it will become PV by T is equal to constant, because pressure, product of pressure and volume is constant, product of uh, sorry, ratio of volume and temperature and ratio of pressure and temperature, they are constant. So PV is by T is equal to constant. So this means that if I've got P1 V1 by T1, this will be equal to P2 V2 by T2. Looks like you already know this thing, right?
Yeah.
Okay. Uh, that's it, I think, in this particular chapter. Let's move to the questions of this one. Can you do this one? There's just one in this one. Okay. This one, question number one.
Question one. Okay. Wait, so what would I do? Because I know like P1 times V1 equals P2 times V2, but like how do I?
Hmm. All right. So this particular question, it says a certain quantity of a gas has a volume 30 cm cube. So let me write that. I have got V1 is equal to 30 cm cubed. Then the next thing that is given is, next thing given is that um, pressure is 1 into 10 raised to the power 5 pascals. So P1 is equal to 1 into 10 raised to the power 5 pascals. So then we are given, then we have to calculate volumes at two different pressures. So P2 is given, P2 is given, first P2 is given as 2 into 10 raised to the power 5 pascals.
Mm.
Okay, so we have to calculate what would be V2. Okay, the gas law, what was it? P1 V1 is equal to P2 V2. Simply looking at the question, I know that pressure, it has doubled. So from 1 into 10 raised to the power 5, it has gone 2 into 10 raised to the power 5. So if pressure
Yeah.
doubles, the volume would halve, right?
Okay.
But
So
let's
15.
15. But let's see 15 cm cube. But let's see with the help of formula, if I've got P1 V1 is equal to P2 V2, and to calculate V2 I have to isolate it. So P1 V1 by P2 is equal to V2. Therefore V2 is equal to, P1 is 1 into 10 raised to the power 5, 1 into 10 raised to the power 5, V1 was how much? 30 cm cubed.
Mm.
I didn't convert cm cubed into meter cubed, so the answer that I'll get is also in cm cubed. And V1, sorry, I have to divide with P2, which would be, sorry, 2 into 10 raised to the power 5. 2 into 10 raised to the power 5. So these two cancel out. 30 by 2 will be equal to 15 cm cubed,
Mm.
as
Okay.
as expected. So now for this one,
Wait, can you go back 1 second?
sure, sure, sure.
Okay.
Okay. So the second one, I know initially the pressure was 1 into 10 raised to the power 5. If it becomes 5 into 10 raised to the power 5, the pressure has increased 5 times. The volume
Mm.
would decrease by 5 times, right?
Yeah.
So it would be 1/5. But let's put the values in the equation and let's see if we get the same answer through equation as well. We would, but would you like to give it a go?
Sure. So 6.
Um, yes. So quickly, this P2, since it has now become 5 into 10 raised to the power 5, this thing would become V2 is equal to hmm, P1 V1. So P1 is how much? 1 into 10 raised to the power 5. V1 is 30 by 5 into 10 raised to the power 5. Again, these cancel out. 30 by 5. V2 is equal to 30 by 5 is 6 cm cubed. Alright.
Mm.
Next thing that we have is thermal expansion. So we know solids when heated they expand, right?
Yeah.
If we apply more heat to any metal, it would expand. This phenomena of expansion is used in a number of applications. So, for example, when we have to fix uh, one metal into another, so we have got this mold in the axle of the engine that we have. So this sort of pattern is over here, and in the same pattern something we have to fix in between this thing. So we will expand this one, or we will put the other metal which we have to put inside it. We will reduce the temperature, expose it to very cold temperature. That particular metal, it would shrink. We would put inside it, and then as it expands it would get fixed in this thing, right? The same phenomena, it's used on rail tracks as well. So for example, if you have ever seen the track of railway somewhere, you would have noticed that there are spaces in between metals. metal
Yeah.
rods that are lead. So it is to allow for thermal expansion, that whenever temperature rises, the rail track does not get damaged. If it were just one single piece of metal, when it expands, it would break. At points, it would go up and it would break. Or if the joints they were put together, the metal on the both sides of the joint, it would expand and the track would not be usable. All
Yeah.
right, this thing. Then what else? What else? We have got bimetallic strips. Bimetallic strips, they are used in switches. So for example, a heat switch, they in thermostats. So if I want to switch to turn on after reaching, or it I wanted to turn off after reaching a certain point of heat. For example, in case of iron that we have, so iron used to iron clothes, that iron. So we have the thermostat in it, which uses a bimetallic strip. So as it reaches a temperature, there is a bimetallic strip. So there are two metals on it. One, it has got a higher melting point, or it, let's say, not melting point, uh, it quickly expands as compared to the other metal it is attached to. So the point of using two metals instead of one is that if it were just one metal, it would expand. When these two metals are put together, the strip, it would bend. Let me show you. So this is the copper and iron strip, and both copper and iron, they have got different temperatures. I mean, same temperature provided to both of these would cause different expansion in both of them. All right. So when I heat this thing, it turns this way. So if the switch were over here, after reaching a certain heat, it would bend and the switch would turn off.
Okay.
Okay, so this is the use of bimetallic strips. It's used in fire alarms uh, as well as in thermostats. The next thing that we have got is thermal expansivity. So anybody who is building some structure, they have to allow for that structure to expand. For example, here the example is given of a bridge. So the engineer who is designing the bridge, he has to account for three things. Number one, length of the bridge. Number two, the what's the highest and lowest temperature that this bridge will be exposed to. And thirdly, the material which is used within this bridge, for these ranges that it would be exposed to, how much will it expand by. This is called linear expansivity. And if you could please take down the definition and formula of linear expansivity from over here as well.
Okay. Okay, I wrote it down.
Uh, let's move on to the questions for this chapter. For water, there is, all right, usually materials they contract when they are exposed to cold temperatures and they expand upon heating. For water, it shows a dual behavior. For water, when, for example, at room temperature, let's say room temperature is 20 degrees centigrade or 27 degrees centigrade, if I cool down the water until it reaches the temperature of 4 degrees centigrade, it contracts. But
Hmm.
when it I lower the temperature further from 4 degree to 0 degree centigrade, it expands. All right, this is called
Okay.
anomalous expansion of water. What any material, it shouldn't be expanding when its temperature is lowered. However, for water from 4 degrees centigrade to 0 degrees centigrade, when the temperature is being lowered, it expands. And suddenly, upon reaching 0 degrees centigrade, from 0 to -4, it again starts contracting.
Hmm.
Okay, so the maximum density of water is at 4 degrees centigrade because that is where it has contracted to the most. Also, you might have noticed if you have got this ice frozen in a particular container, you put water in a container and you put it in freezer for the water to freeze. You must have noticed that there is usually a bump at top of this, for example, upwards bump at the top of this ice surface. Have you ever noticed that?
Yeah.
It is because of this anomalous expansion of water that when it's going from 4 to 0 degrees centigrade, water is expanding. So since it's expanding, I mean, if the container is filled, it might spill out from the side, or usually it expands, and at the center of that thing you have got an upwards hump. So this is for water. Obviously, if we have got a pond, and in that particular pond the water with 4 degrees centigrade temperature would be at the bottom because it is most dense.
Hmm. Okay.
Okay. These questions, if you could give explanations verbally, perhaps.
Okay. Because it like the metal expands.
Hmm. The metal
Like
expands,
when
so
you
its grip
expand.
over the glass would loosen.
Yeah.
All right. Next.
Because it expanded a bit and then when you
Hmm.
sit on it, it's
Hmm. Even if you don't sit on it, sometimes during night you suddenly hear a voice and there is nobody around and it's just furniture or floor. If it's made of wood, it creaks. It's because of this that it has expanded during the day, and now when it's contracting, the wood makes that noise.
mm,
The same thing for the
that's
roads
cool.
as well. I told you the same way they leave a gap in between um, adjacent rail patches that they are putting, the metal patches for railway track, they sometimes leave for the road as well in between some gaps, so that when this concrete it expands during the hot day, the road wouldn't break. If they leave no such
Mm,
patch, it would expand and it would be, I mean, it would be causing damage to the road. In between at places there would be patches where it gets broken. Question number two, please. Would you need this diagram as well? Okay, let me see. out of these two, for the same temperature change, which out of these two is expanding more? Aluminium and copper.
The aluminium.
Aluminium is expanding more. And if I reduce the temperature, which one would lose temperature more?
Mm,
It would be
then the copper.
the
Mm.
same, aluminium. All right. So aluminium, since it would contract more, would it cause it to? Mhm. It would cause it to bend the other way.
Okay.
All right. Question number three. Just a second. Just a second. What did this question say? To show would appear if it were cooled below room temperature. Hmm. 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 It would bend the other way. You understand that why, right?
Yeah.
All right.
C.
It will be B. The reason is this formula that your linear expansivity, original length, and temperature rises. So expansion is more if original length is more. Similarly, expansion is more if temperature change is more. Right? This C option said 2 and 3. No, if it has a larger diameter, it won't expand as much. It won't expand as much because see the change in length we have to give, right? Since the larger diameter thing, it would require more heat for the same, I mean, to cause the same change in length. Do you get this thing?
Mm.
So it would be 1 and 2. Fourth, please.
Is one correct or not?
Hmm, it is correct.
Then A.
Hmm, let's say because all else is based on one. That is how thermostats work, right? Bimetallic strip which would bend away upon rise of temperature. Okay. And metal A would expand more since it's bending away, so it's upwards. This up thing would bend more. All right, any other, no other questions in this one? The next is a small topic with regards to thermometers. Thermometers are the devices that we use to measure temperature. Usually the unit that we use is Celsius. You know the conversion from Celsius to Kelvin and vice versa. So C minus 273 is Kelvin. When it's minus 273 degrees centigrade, the temperature in Kelvin is 0. So whatever the temperature in degrees centigrade, I subtract 273 from it to get Kelvin. C plus 273. C plus 273 is Kelvin. Hmm. Okay. Then there is this scale and unit of temperature. We have to get the highest point and the lowest point, which has to be shown by this particular temperature. So this one over here, it shows degrees centigrade 0 to 100, and then we take the space in between and we divide it, so that would give me scale that each rise in point is showing me how much change of temperature. All right, so this particular thermometer, it can show me the lowest value of 0 degrees centigrade, and it can show me the highest value of 100 degrees centigrade. Any temperature lower than this or higher than this cannot be calculated using this particular thermometer. Okay, this is liquid in glass thermometer. So in this glass casing, there is this another glass casing, and this one, it has got a liquid filled in it. This liquid is usually mercury, but sometimes for lab, for experimentation, we use alcohol thermometers. Alcohol, it changes the reading very quickly. Mercury, it changes some time too. For example, at home when we are, or at hospital when we are checking the temperature, the doctor puts a thermometer in the mouth of the person, if it's not digital one, for let's say a minute or two. So that's the amount of time it takes mercury to expand to whatever temperature we are expanding it to. Alcohol, it changes its value in seconds. So in order, for example, if I'm heating something in a beaker, and right when it starts boiling, I want to note the boiling point. So if the thermometer is giving me the reading at that exact point, then the thermometer is useful. If the thermometer would show me reading after 2 minutes, and after it starts boiling 2 minutes later, I will get the correct reading on the thermometer. That is why in labs, when we are doing experiments, we don't use thermometers with mercury in them. Did you understand this last thing, why we use mercury? Okay. So those alcohol thermometers we use. Then there is this thermocouple, clinical thermometer. It has higher sensitivity. Do they mention the liquid in it? They don't. Removed after 1 minute. That thing. Okay, we have got this thermocouple thermometer. So it uses, for example, here is the hot junction, here is the cold junction. So I'll connect the wires at the two end, and it will give me the difference between the two ends. Okay. Uh, Questions on it. For heat, we know it passes from the body with higher temperature towards the body with lower temperature. Heat is also called thermal energy. All this you already know. Um, in order to make that will small changes. Hmm. Question number one and two. Let's see. Yes, question number one and two, please. In Egypt, we also use degrees centigrade usually, right?
Degrees what?
Degrees centigrade to measure temperature.
Yeah.
In just in US, I think they're using degrees Fahrenheit.
Yeah.
So it's funny asking someone what's the temperature over there like.
It'll be like 90.
Hmm. Hmm. Hmm.
So iron would probably be the 1500 one.
Hmm.
Room temperature, isn't that like 27 or something?
And room temperature usually is 27, but comfortably warm, that would be, I think, 37 degrees. No,
Yeah.
uh, 19 degrees. 37 degrees would be too hot. It's like very hot. I mean,
Yeah.
a hot day is like 37 degrees.
19.
19.
0 for ice.
For ice melting, yes, 0. There is, I think, a funny bit of information. Usually, we take the melting and freezing point as 0 degrees centigrade, whereas in reality, I think ice actually melts at water freezes at -4, and ice melts at 4.
Really?
Hmm.
Why did we do 0?
Because it's convenient. The same way we use 10 instead of 9.81 for G. If we have to be very precise in calculating, I mean in the readings of temperatures, then we use those readings. Otherwise we simply use mean value 0, because for most of the objects the melting and freezing point is the same. That's the way for most of the objects. For water it's different. I don't know of any other material which has the same property. There could be. I'm unaware of any other.
Hmm. -12,
-12 for
the lowest temperature.
the lowest temperature are recorded in London. Hmm.
Okay. Body temperature, that's 37.
That's 37. Okay. Question number two, please, quickly. Is somebody running a drill machine in the background?
Yeah, the neighbors.
hmm You live in an apartment, right?
Yeah.
That's. I used to live in an apartment. I lived over there. I mean, in different apartments. When I was in Karachi, we lived like for 15 years in different apartments. So the way you behave with regards to sound and how much of it goes to the other apartment, you have to be conscious of that a lot. Changes a lot when
Yeah.
you move to a bungalow.
Mm.
C. Hmm. That's the tube within the glass in which liquid is contained. That's called capillary tube. The tube, this thin tube within the glass, this over here, this is called capillary tube. Capillaries, are those the vessels which connect veins to arteries, right? In bio, we study that there are veins, there are arteries, and their function is to make the deoxygen to carry if there is any uh, arteries have got oxygenated blood, so if any becomes deoxygenated, they are the ones which transfer it to veins, right? Hmm. Hmm. They are the thinnest out of the three. Okay, so for this one, you decrease the diameter of the capillary tube, and on the same length, you'll be able to get more readings, since the same temperature change will cause it to increase more height or lose more height within the capillary tube, right? So you would be able to measure more small changes. Any other question? Okay, question number 3 and 4. Hmm. This is a bit confusing. The property, it must change with temperature. So those properties of materials which do not change with temperature, we cannot use those properties to measure temperature. For example, expansion. We know that materials, they expand when heated. So we can rely on this expansion to calculate temperature change. So, for example, color of of a particular substance, if it does not change with temperature change, we cannot rely on this color for measuring temperature change. For some things, it does change. So, for those materials, we can rely on the change of color to measure temperature of that particular substance. So, the property, it must change with temperature so that we can rely on it to calculate how much it changes with how much temperature rise or fall, so we can then use that to measure. And it must continuously change for temperature. For example, if the temperature change that I'm measuring, it is let's say 10 degrees centigrade, and the property, it only changes over 5 degrees centigrade of temperature but for the other 5 it does not change, then I cannot rely on this particular property to measure the temperature change. So it must change continuously with the change of temperature. So for example, these liquids that we use within the thermometers to calculate change of temperature, these liquids, they have got their own boiling points. So if we are to measure a temperature beyond the boiling point of that particular liquid, for example, alcohol, what was the boiling point of alcohol? It was quite low. Um, Boiling point of alcohol is 78.37 degrees centigrade. So I cannot use alcohol as a substance in the thermometer to accurately measure a temperature of above 78.37 degrees centigrade. So they to measure those changes, I think we use mercury or some other substance, usually mercury, but not even mercury, because mercury, it responds very late to change in temperature. Anyhow, alcohol cannot be used for a temperature higher than that. Okay, the properties over here that you have to give in part B that qualify or that can help us measure the change of temperature are we have studied volume, resistance, and pressure. So we understood when we studied those gas laws that when temperature changes, pressure changes. Similarly, when temperature changes, volume changes. It applies to the liquid as well. And the third property is resistance.
Resistance?
Hmm. In metals, resistance it increases with increase of temperature. I think it increases because with increase in temperature, the metal atoms, since we know from the previous chapter that any solid, its molecules are continuously or atoms are continuously vibrating. So when I
Okay.
increase the temperature, that vibration it goes higher, and then it becomes more difficult for the electrons to flow through the metal. Therefore, the resistance of the metals it increases when I increase the temperature.
Okay.
Okay, the next one. If we have to measure a temperature of 1000 degrees centigrade, which thermometer do you think we'd use? We'd use a platinum resistance temperature for this particular thing, for this high temperature. For this high temperature, we use a platinum resistance temperature. For changing very small changes in temperature, very small minute changes in temperature, we usually use thermocouple.
Okay.
And for the third one, we would use alcohol temperature. Sorry, alcohol thermometer.
Hmm.
All right. Uh, clinical. Could you take a screenshot of this one? Sometimes this thing gets tested. Clinical thermometer, or you could read it right now. If you want to note anything, you can. Um, it's a simple theory.
Okay.
Done.
1 second. Yeah, okay.
Okay, the next thing is a new topic. Shall we start today or the next class?
Next class, because it's basically almost time.
All right, all right. See you then next Thursday, inshallah.
Yeah.
All right, bye.